Welcome back to the channel. Today, we are diving into one of the most fundamental topics in biomedical engineering, bioelectric signals and electrodes. We'll explore how our bodies act as biological batteries and the technology we use to capture those signals for medical diagnosis. A biomedical signal is essentially a collection of data that tells us something about a biological system. In the human body, these signals are usually electrical, like the ECG for your heart, the EEG for your brain, or the EMG for your muscles. These signals are the primary language doctors use to listen to your internal organs. To understand these signals, we have to look at the cellular level. Every living cell acts like a tiny battery. Because of the way ions like sodium and potassium are distributed across the cell membrane, a resting cell has a negative charge inside compared to the outside, usually around -90 millivolts. This state is called polarization. When a cell is stimulated, the membrane suddenly allows ions to rush in. This flip in electrical charge is called depolarization. The potential jumps from -90 to about +20 millivolts. This rapid change, followed by the cell resetting itself, repolarization, is what we call an action potential. This is the spark of life. The ECG is perhaps the most famous bioelectric signal. It isn't just one cell, it's the combined electrical activity of millions of heart cells. The P wave shows the top of the heart contracting, the QRS complex is the big squeeze of the ventricles, and the T wave is the heart resetting for the next beat. Moving to the brain, we find the EEG. Unlike the heart, these signals are incredibly faint, often less than 100 microvolts. Because they are so small and buried under the skull, recording them requires very sensitive amplifiers and specialized electrodes. Brainwaves are categorized by frequency. Delta waves occur during deep sleep, while alpha waves appear when you are relaxed but awake. If you're solving a hard math problem, your brain is likely buzzing with beta and gamma waves. These frequencies give us a window into a patient's state of consciousness. So, how do we get these signals out of the body and into a computer? We use electrodes. An electrode acts as a transducer, converting ionic current, flowing inside the body, into electronic current that can flow through wires to our medical instruments. When you put a metal electrode against the skin using a conductive gel, a chemical reaction occurs. A charged double layer forms at the interface. This creates a small voltage called the half-cell potential. If this potential is unstable, your medical reading will be full of noise. Engineers model this interface using the Warburg equivalent circuit. We treat the connection as a combination of capacitors and resistors. The important thing to remember is that this impedance changes depending on the frequency of the signal we are trying to measure. Electrodes can be polarized or non-polarizable. Perfectly polarized electrodes act like capacitors, they don't like to let DC current through. Non-polarizable electrodes, however, allow charge to cross the interface freely. For most medical applications, we want electrodes that are as non-polarizable as possible. The industry standard is the silver chloride electrode. It's highly stable, has a very low half-cell potential, and produces very little noise. This is why you see them used in almost every hospital around the world for ECG and EEG recording. To make these, we take pure silver and deposit a layer of silver chloride on it through a process called chloriding. The thickness of this layer is crucial. Too thin and it wears off, too thick and the impedance increases. The sweet spot is usually between 100 to 500 milliamps per square centimeter. The skin is naturally a poor conductor. To fix this, we use electrode jelly. This jelly contains chloride ions that bridge the gap between your skin and the metal electrode, ensuring the signal passes through clearly without losing its strength. If the patient moves, the electrode shifts, and the chemical equilibrium at the skin is disturbed. This causes motion artifacts, those messy squiggles you see on a monitor when someone moves. Proper skin preparation and stable electrodes are the only ways to fight this. For a standard ECG, we use surface electrodes. You might see metal plates for the limbs or suction, Welsh cups, for the chest. These are great for quick diagnostic checks, but they aren't ideal for long-term monitoring because they can slip or dry out. To reduce movement noise, we use floating electrodes. Here, the metal doesn't actually touch the skin. It sits in a recessed pocket filled with jelly. This cushion of jelly helps keep the signal stable even if the patient is moving around. In modern hospitals, we mostly use pre-gelled disposable electrodes. They are cheap, sterile, and come with a sticky foam pad that stays in place during exercise. After the test, you simply peel them off and throw them away. Innovation is moving fast. Systems like the SmartPad use conductive fabrics. A patient can simply lie on a pad, and it will pick up their ECG through their clothes using an array of sensors. No sticky pads required. We are also seeing the rise of dry electrodes, which use the body's natural perspiration as the electrolyte. Even more advanced are capacitive electrodes, which don't even need to touch the skin. They can sense the heart's electrical field from a short distance away. When we need to look at specific muscles, like testing for nerve damage, we use needle electrodes. These are inserted directly into the muscle tissue to get a much sharper, localized signal than a surface pad could ever provide. There are three main types: monopolar needles, which are simple coated wires; bipolar needles, which have two wires inside; and concentric needles, where the recording wire is inside a hollow needle that acts as the ground. Each has a specific use in clinical neurology. If we want to get even smaller, down to the level of a single neuron, we use microelectrodes. These have tips so fine they are measured in microns. They allow researchers to listen to the firing of a single brain cell. These can be made of metal needles drawn to a fine point or glass tubes filled with salt water. Metal microelectrodes are tougher, but glass ones are better for recording steady-state signals without drifting. That's it for today. If you're now an electrode expert, hit that like button and subscribe to join our Biomed community. Got questions on signals? Drop a comment. I read them all. Check out the next video on the screen to keep learning. Thanks for watching, and I'll see you in the next one.